What's up, everybody? In this video, we're going to be covering USACO's 2022 January contest at the silver level. Problem number 2, cow frisbee. Farmer John's N cows, where N is less than 3 times 10 to the 5th. Okay, so just make a note of that. 10 to the 5th means we can't use an O of N squared algorithm. O of N squared would be 10 to the 10th, so that'd be too large. The N cows have heights 1, 2, up through N. So every cow has a distinct height. The first cow has height 1, the second cow has height 2, all the way up to N. No duplicates, no skipping. One day, the cows are standing in a line in some order playing Frisbee. Let H1 to Hn denote the heights of the cows in this order. So the H's are a permutation of 1 through N. Okay, so the cows are standing in a line. I've got the H1 cow first, and then the H2, H3, H4. But their heights are not necessarily in order. For example, this could be the cow with height 4. This could be the cow with height 1. This could be the cow with height 3. And this could be the cow with height 2. 2 cows at positions I and J just means at any given position, some position I and some position J, maybe I here and J here, for example, in the line can successfully throw a Frisbee back and forth if and only if every cow between them has a height lower than min of HI and HJ. All right, let's pick that apart. So if, for example, I is here and J is here, that means that these 2 cows can throw the Frisbee back and forth if and only if every single cow in between them is shorter than the shortest between the 2 of them, which would mean between 4 and 3, the shortest one is 3, which would mean that as long as every cow between them is shorter than height 3, they can throw a Frisbee. So in this case, the H1 cow and the H3 cow, which have heights 4 and 3 respectively, are able to throw the Frisbee because the cow in the H2 location has a height of 1, which is shorter than both of them. Essentially is what that's saying. Let's look at an example where they can't throw a Frisbee. So let's say, for example, obviously 1 and 2. If my I was at H2 and my J was over here at H4, then these 2 cows cannot throw a Frisbee because 3 is not shorter than the shortest of them. In fact, it's not shorter than either of them. But something to watch out for that trips a lot of people up on this problem. Let's look at the cows 4 and 2. Now, at first, you might think that because this cow is taller than this cow, that you'd be able to throw it over. But in fact, because the shorter of the 2 cows is cow 2, we can't throw over cow 3. So even though one of the cows is taller, they both have to be taller than all of the cows. So this is just something to watch out for. I've seen a lot of people trip up on this. All right, let's resume reading. Please compute the sum of the distances between all pairs of locations such that I is left of J. The reason I want to have I less than J, they just want to make sure we don't double count. So if I is here and then J is here, we count that distance. We don't want to then accidentally have it reversed, where then this is cow I, and then this is cow J, and we say, well, I and J are different, and then we're counting that also as a second throw. At which there resides a pair of cows that can successfully throw the Frisbee back and forth. So we got to do the sum of the distances, not the number of pairs, but the sum of the distances between the pairs. Additionally, it says the distance between locations I and J is J minus I plus 1. This is another thing to watch out for. I've seen a lot of people get tripped up on this. The reason why is because if you think about the distance from here to here, H1 to H3, you would think that would be a distance of 2, but they actually want it represented as 3 minus 1 plus 1, which is equal to 3. So essentially what you're doing is the number of cows that are involved in that range, including the first cow, including the last cow. So that's a distance of 3, not a distance of 2. We can't just do I minus J. We have to do I minus J plus 1. Input format. The input format arrives from the terminal in standard in. That's just going to be typing into the console. The first line of input contains a single integer n. Remember, that's how many cows there are. It's this guy right here. 7 cows in this example. The next line of input contains H1 through Hn. These are all of the heights of the cows that are standing in a line, and this is the order that they are standing in, separated by spaces. The output format, print output to the terminal, again, just printing it to the console. It says output the sum of the distances of all pairs of locations at which there are cows that can throw the Frisbee back and forth. Note that the large size of integers involved in this program, because remember, we're going to go up to 10 to the 5th, which is 300,000 in this case. let me see. Note that the large size of the integers involved in this problem may require the use of a 64-bit integer data type, aka a long. If you're in Python, you don't have to worry about that. So let's look at what that means. Essentially, if we have 300,000 total cows, and possibly quite a few of them are capable of throwing back and forth, I would say at most, it sounds like we're going to have about 300,000 squared possible is that possible pairs? It would be lower than that, but it would be a large number of pairs. And then we're also measuring the distance. So yeah, that's going to go way above what an integer can do. And just a reminder, with a standard integer in Java or C++, we only get up about to 2.1 billion. Is about as large of a number we can store. It's 2 to the 31st power. When you get to 2 to the 31st, that's as large of a number as you can store in an integer before you have an overflow. So if you're working in the billions, you probably don't want to be using integers. If you haven't worked with longs before, all that long is essentially an integer that can be a lot bigger. We still don't have decimal places on them, but they behave exactly like integers. You can declare them like integers. It's just going to be long, like x equals, and then you would just put whatever the number is. Okay, so for this example, and actually on all of these examples, I'm going to display the heights sort of like a bar graph, because I feel like that's a really easy way to visualize what's going on. So the first cow here has a height of 4. We'll make a bar graph that goes up to 4. Next one is 3. Next one is 1. And there's 2, which is a little bit taller. Then there's 5, 6, and 7. All right. And as we were talking about earlier, just to watch out for, certain pairs can throw, certain can't. We can only throw if every cow between us is smaller. So for example, from here to here, that's a valid throw. Those cows can throw to each other. But from here to here, that's not valid. Now, again, I mentioned this before. It looks like it might be valid because 4 is quite tall, but this second cow, remember, has a height of 3, and this cow over here has a height of 2. Because the 2 is shorter than at least one of the cows in the middle, that's not a valid pair for throwing back and forth. So let's kind of just try and eyeball this and see where the pairs are going to be. And they do have them printed down below, but let's not look at this quite yet. Let's try to just do this visually and make sure we understand the problem first. So our first cow, let me see. I don't know why that won't erase. Okay. Our first cow here is going to be able to throw to its immediate neighbor. And in fact, every cow can throw to their immediate neighbor because there's no possible way that there's a cow between them that's taller. It cannot throw to any of the other 2 down here, but it can throw to this one. And it can't throw to the one behind it because the cow right behind it, again, now we're running into a problem where we would have to throw over a cow that's taller than one of the cows. This would be a cow in the middle that's taller than the 4. So, again, just kind of watch out for that when you're trying to solve these. Second cow can throw to its immediate neighbor. It can also throw over that one because they're both taller than it. And it can throw to this one as well because both this one and this one are taller than both of the ones in the middle. So that's a valid pair. We have this one down here throwing to its immediate neighbor, but because its immediate neighbor is taller than it, it can't throw over it. This one here also throwing to its immediate neighbor, but because the neighbor is taller, it can't throw over it. This one can throw to its neighbor, but not over it. This one can throw to its neighbor and not over it. And then again, because these ones are tall, this one on the end here, for example, is tall, but because everything that it could throw to would have to throw over this one, and this is the second tallest cow, everything past that's going to be too short. So none of those are going to be valid pairs. All right, so let's kind of just look at this here. I've got this first one here is 1 to 2. I've got 1 to 5, it looks like. I've got 2 to 3. I've got 2 to 4. I've got 2 to 5. I have 5 to 6. And I have 6 to 7. All right, let's look back at this and see how close we are. So I got 1 to 2. I got 1 to 5. 2 to 3. 2 to 4. 2 to 5. I missed 3 to 4. 3 to 4. Ah, yeah, this one right here. 3 to 4. That's 1. 4 to 5. Yeah, I missed the neighbors. 4 to 5. 5 to 6 and 6 to 7. So as you can see, there's a lot of bookkeeping here, and this is hard to keep track of. So you have to be really careful when you're doing this. And even now, just as I'm demonstrating, and I missed 2 of the neighbors. So moving on to the algorithm for this, we need to try and figure out a way that we can analyze this, but not in n squared time. Now, If we were allowed to do this in n squared time, this is actually a very easy problem in n squared. Let me clean this up here real quick. Essentially, what you would do with n squared time is you would have a for loop with I going from 0. Let me see. I would be going from 0 up to whatever n is. You would have j going for I plus 1 up to whatever n is. You would have k going from I plus 1 up to j minus 1, I guess. And then you'd have some sort of an if statement in here where if the cow at location k is taller than either the cow at j or the cow at I, then in either situation, that's not a valid pass. And if you're able to get all the way through and none of the cows are taller, then that's a valid pass. So while that's an easy thing to do, this is that might be n cubed time. This is going to be way too slow of an algorithm. What we really need is a linear algorithm, or at most an n log n algorithm. And actually, there is a linear algorithm for this. Now's a good time to take a minute if you want to pause the video and play around with this with paper pencil, and then I'll start digging into. We can dig into it together. All right, so as we're drawing these bars, let's try to think of just every possible scenario we might have. If I have a scenario where I've got a cow at some height and the next cow is shorter, that means that there should be at least one cow that is taller than this cow, if there is any cow that's taller than that cow, to the right side of it that I'm able to throw to. So then say like I've got a bunch of cows that are just of different heights. I'm not going to be able to throw to any of them if this one is taller. But eventually, at some point, I'm going to come to a cow that's taller than this one and or taller than that one, unless it's decreasing all the way down. If that's the case, then that means that this cow would be able to throw over all of those to that one, as long as all these cows are shorter. Eventually, when we come to a cow that's taller than it, that's the cow it's going to be able to throw to. If that cow is taller than it, then any cows behind it cannot be thrown to. Let's look at another situation. So like I have a cow here, and then I have a short cow, and then I have a cow that's kind of in the middle, shorter than the first cow, but taller than everything between it. Then that's going to be a valid pair, but this one still has the option to potentially throw to more cows behind it. For example, there's a cow here, I could throw to that one as well. There's a cow here, as long as it's shorter, I could throw to that one as well. We always can throw over the shorter cows until eventually I get to a cow that's taller. Now, once I hit a cow that's taller than this cow cannot throw to anything behind that cow. Anytime you hit a cow that's taller, that's a wall, and we can't go past that wall. Let's look at a couple more of these. If I have constantly increasing, for example, if this cow is taller, I can throw to it, but I can't throw to anything behind it. That also means that nothing behind it can throw to it. So even if the very next cow is like 100 feet tall, these can't throw to each other because this one is taller than this one. So that's ultimately what you're tasked with trying to do, is try to keep track of all the cows that potentially can throw a Frisbee to a cow that's further down the line, and then keep count of what those distances are as you go. Let me back up here to that original example. All right, so let's figure out how we're going to turn this into an algorithm. If you think about it, what we've pretty much established is that for every cow, when they're throwing, they're going to have at most one cow that's taller than them that they can throw to. There may be multiple cows that are shorter than them, though. For example, in the case of the cow in position 2, the cow in position 2 is going to have a throwing pair with these 2 cows. But from each of those cows' perspective, there's only one taller cow that they can throw to. Anytime you have a cow, regardless of their height, throwing a Frisbee, there only can be one taller cow that they can throw to. Because once they throw to that first taller cow, anything behind them is going to be inaccessible. And that's going to be the same going from right to left. If I have any cow that is, for example, shorter here, rather than thinking of it from the standpoint of this cow is going to throw to the shorter cow, think of it from the standpoint of this taller cow is the only cow that this shorter cow is going to be able to throw to. And if we do that, then we've got a really nice linear time algorithm using a stack. Essentially what's going to happen is, and let's just real quick eyeball this and make sure. So what's going to happen is this cow right here is going to, the one taller cow they're going to throw to is here. This cow, the taller cow they're going to throw to is here. This one will throw here. This one will throw here. This one throws to here. This one throws to here. That's going to give us the pairs 1, 5, 2, 5, 3, 4, 4, 5, 5, 6, and 6, 7. And then we're gonna have to do the same thing going from right to left as well. Because for each cow, we found the cow to the right that was taller that it can throw to. Now we have to find for each cow the cow to the left that's taller that it can throw to. We can just kind of see that 7, 6, and 5 aren't going to have anyone to throw to because there's no taller cows. The cow in position 4 will throw to 2. That's the 2-4 pair. The cow in position 3 will throw to 2. That's the 3-2 pair. The cow in position 2 will throw to 1. That's the 1-2 pair. And then no further throws from right to left because cow in position 1 has no one to throw to. Let's double check and make sure we caught all those, and then we'll run through how to do this with the stack. Okay, so I've got 1, 2, check. 1, 5, check. 2, 3, check. 2, 4, check. 2, 5, check. 3, 4, check. 4, 5, check. 5, 6, check. 6, 7, check. Fabulous. Okay, so we got all of them. All right, let me back that back up. I'm going to clear out the left side here. Just erase that, be faster. All right, let's see how to do this with a stack. So what's going to happen is every time we encounter a shorter cow, it goes on the stack. Every time we encounter a taller cow, we pop all of the shorter cows off the stack as if to indicate that taller cow has been thrown to by all those shorter cows, and those shorter cows now can't throw to anybody else. So essentially what we're keeping track of in our stack is a stack of all of the cows who potentially could throw to some taller cow. And I'm going to put both the position and the height in here. There's a lot of ways you can approach organizing this information. For example, you could build yourself an array that keeps track of indexing the position of the cows based on their height. So for example, the cow in index 4 would be position 1. That would indicate that the cow of height 4 is in position 1. And then later, given the height of a cow, if I find a cow with height 4, then I can put that in position 1. If I were to do that, 3, 2, 1, 5, 6, and 7, then the cow of height 1 is in position 3. The cow of height 2 is in position 4. The cow of height 3 is in position 2. And then 5, 6, and 7 are the same. If I do that, then in my stack, I only have to keep track of heights. And then later, when I say, oh, I've got a height 4 cow, I can just look in this array into index 4 and see that that should be in position 1. You could also use a dictionary for that. You could store a list of pairs or tuples, potentially. But essentially, we need a way to be able to go from the height of the cow to the position of the cow. I'm going to go ahead and just do a list of pairs because that's the easiest thing for me to visualize. So I've got 4 and then 1. That indicates that there is a height 4 cow in position 1. That goes into the stack. Next cow is going to be height 3 in position 2, which is shorter. So it's not going to block 4. The height 4 cow is not going to throw to it. Another shorter cow, height 1 in position 3. These are all now 3 cows, 1, 2, and 3, that have yet to find a taller cow to throw to. So we have to keep track of them because sooner or later we will find that cow that will be their taller cow. We get to height 2 in position 4. That is taller than the height 1 cow, which is at the top of the stack. And we only ever have to look at the top of the stack because we can't put a larger number on the stack. These are always going to be decreasing in height. It's like a Tower of Hanoi kind of thing. As we go up through the stack, we'll get to shorter and shorter cows. If we have a larger, taller cow, that's going to be removing items from the stack until it gets to one that it's not taller than any longer. Anyway, so we got to the position 4 with height 2 cow. That height 2 is taller than height 1, so that's our first pair. As long as we can go from height 1 to the position, again, if you have an array where index 1 is going to be 3, or if you want to just keep a list of pairs, that's what we're storing. So this is a throw between 3 and position 4. That removes the height 1 cow from the stack, but now the height 2 cow, which is in position 4, has to insert herself into the stack, height 2, position 4, because now she's going to try and find a taller cow to throw to. Moving on to the right, we get to position 5. Position 5 has height 5. This is actually going to clear our entire stack. So looking on the top, height 5 is taller than height 2, so that's a throw between 4 and 5. That's this throw right here, by the way, since finding that taller cow can't possibly throw to anyone behind that cow, so we don't need to keep that cow in our stack anymore. Same thing with the height 3 cow in position 2. Is going to throw to this cow and then can never throw to any further cows that we're going to come across later. So remove from the stack. I need to be writing these down. That's from 4 to 5, from 2 to 5, and then finally from 1 to 5. And then the height 5 cow now has to insert itself in the stack to find a taller cow to throw to. Okay, let me see. 2, 5, 3, 4, 4, 5. I'm just doing a quick sanity check to make sure we got all of them. So yep, it looks like I got this one, I got that one, I got that one, and I got that one so far. So we're in good shape. All right, moving right along. Cow 6, 6. 6 is larger than 5, so that's going to be the 5, 6 pair, 5, 6. And then the 5, 5 comes out of the stack, and the 6, 6 will go into the stack. Then 7, 7. So that's going to be my 6, 7 pair. 6, 6 will come out of the stack. 7, 7 goes into the stack. And then we've reached the very end, which means 7, 7 couldn't find anyone to the right that was taller to throw to, which makes sense, obviously. 7, 7's on the edge and is also the tallest cow. All right, going from right to left now. We'll put 7, 7 on the stack, 7, 7. And just kind of keep an eye on these, because you'll notice that they're still going to be there when we get to the end, because they're not going to find any taller cows to throw to. 6, 6 goes on the stack, 5, 5 goes on the stack, 2, 4 goes on the stack as a shorter cow. 1, 3 goes on the stack. It's as tall as we've seen our stack get so far. So far, that's all been, and that makes sense since we're on a decreasing gradient here. So far, we haven't found any taller cows to throw to. All right, now we've encountered a cow in position 2. The position 2 cow has a height of 3. 3 is bigger than 1, so we're going to have a 2 to 3 throw, because that's in position 3, and this one's in position 2, so that's a throw from 2 to 3. 2 to 3. Removes the height 1 cow from the stack, because 1 can't throw to any other cows that we're going to encounter now. And then throw between 3 and 4. Position, 2 and 4. This is position 2 is the cow we're adding, throwing from position 4, which is where the height 2 cow is located. So it's my 2, 4 pair. Then the height 2 cow comes off. And then finally, I've gotten to the 5 that's taller. So now I got to put the 2, 3 cow back on, or not back on, but put the 2, 3 cow onto the stack. So now this cow is going to look for a taller cow. We move on to the next cow. That's position 1, height 4, which is definitely taller. So that is my 1, 2 pair. Put that at the bottom. 1, 2, height 4. I wrote that backwards. That should be height 3, position 2. Sorry. Okay, so then I get to height 4. Height 4 is taller than height 3. So that's going to be a throw between position 1 and position 2. That's my 1, 2 pair that I wrote at the bottom. That removes the height 3 cow. And then finally, the height 4 cow can be placed on the stack in position 1, although we're not going to encounter any further cows. And that shows that traveling from right to left, the cows that didn't have a cow to their left that was taller are in positions 7, 6, 5, and 1. And we can just eyeball that and see that. That's position 1, and then 7, 6, and 5. Every other cow had a taller cow to the left to throw to. All right, moment of truth. Let's see if we caught all of them. Okay. All right, 1, 2 was the very last one I found. 1, 5, check. 2, 3, check. 2, 4, check. 2, 5, check. 3, 4, check. 4, 5, check. 5, 6, check. 6, 7, check. Okay, great, good work. So just as a quick recap, essentially what we're doing is we're doing a linear pass. As we go from left to right, we are keeping track of every cow that potentially might be able to throw to another cow. So keep track of that one, keep track of that one, keep track of that one. When we encounter them, we're stacking them so that we're only keeping whatever the smallest thing is on top. When we encounter a taller cow, we mark the pair, this between the height 1 and the height 2 cow. We remove the height 1 cow from the stack. We place the height 2 cow onto the stack. Here's height 5. That's going to be thrown to from the height 2, from the height 3 and the height 4 cow. We mark those down, pair, 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 and then put the height 5 cow on the stack. Height 6 cow can't go on top of the, remember, we can't put large on top of small. We encounter the height 6 cow. That's the throw between the 5 and the 6. We remove the 5, add the 6. Encounter the height 7 cow. That's the throw between the 6 and the 7. Add the 7. We hit the side. Going back the other way, same exact thing. Here. 7 goes on the stack, 6 goes on the stack, 5 goes on the stack, 2 goes on the stack, 1 goes on the stack. When we encounter the 3, we note the pairing between the height 1 cow and the height 2 cow. Those are these 2 throws right here. Add the height 3 cow onto the stack and count to the 4. Note the pair because 4 is larger than 3. Remove the 3, add the 4. Then we've hit the edge. These cows didn't throw at anyone. All right, good luck coding it, and I'll talk to you guys in the next video.